Hey guys, so this video is about my experience with A-star pathfinding and the jump point search variant of A-star as an amateur hobbyist programmer. So I'm sure there are plenty of inefficiencies and bad design, so feel free to give me any feedback and all that. So if you search online on how to do pathfinding in games, almost always someone's going to recommend A-star. And A-star is a simple pathfinding algorithm, and the Wikipedia page contains a really nice pseudocode section that you can use to prototype A-star if that's something you're interested in. And the section is right here, so really nice. And so what is A-star? So basically it searches nodes and gives them a score based on the cost it took to get there and the cost it'll take, the estimated cost it'll take to get to the goal from that node. And then it compares those node scores to figure out which path to take. There's also things like open sets and closed sets, but to make sure that we don't evaluate the same node twice and all that, but I'm not going to go into too much detail. If you are interested in A-star, there's a ton of great guides online, so check those out. They'll do a much better job of explaining it than I can. Now, the problem with A-star is that it's typically pretty slow by itself, and one way to speed it up is to mess around with the area or the grid that you have to traverse. And one way to do that is to use nav meshes to simplify the area that you have to traverse. So there's a presentation that Valve made about AI behavior for Left 4 Dead, and you can see that in this slide that the area is broken up into rectangular chunks. So instead of treating the area like a grid of tiny little squares, we group them together and form these chunks to simplify the area, which will speed up pathfinding through it. And once you get into how to make these chunks and how to optimally make these nav meshes, there's things called Delaunay triangulation and all that. So there's pretty interesting stuff. But again, I don't know much about it, so I'm not going to go into too much detail about this. So the downside of nav meshes, however, is that they're expensive to generate at runtime. So they're typically baked into the map beforehand. Which means that nav meshes are generally unsuitable for dynamic or procedurally generated terrain because, again, it takes a long time to build them. Another way to improve A-star is to mess with the algorithm itself. And there's been a lot of variants of A-star, all with cute little names. So back to the Wikipedia page, and you can see that there's a little section called variants of A-star, there's the star, ID A-star, so on and so forth. One of the variants that's not listed here is called hierarchical pathfinding A-star, or sorry, hierarchical pathfinding A-star, called HP A-star. And Shining Rock Studios, Shining Rock Software of Banished fame uses this method. So if you don't know, Banished is a great little city building game, and the dev has a blog post where he talks about some of the development challenges that he has and how he solved them. And in this particular blog post, he talks about how pathfinding is slow and how we used hierarchical pathfinding to fix it. I think there's a specific... Yeah, he mentions that pathfinding is slow, and then he figures out how to fix it. And if you look at this picture right here, you can see that the map is broken up into these big squares. And the idea behind HPA star is that you find a path through those big squares first, and then you resolve the detailed path within those big squares. So that's how the Banished dev solved the pathfinding, or dealt with the pathfinding issue. A relatively modern variant of A-star is called jump point search, JPS. And before I show you what that looks like, I want to show you what A-star looks like. So if you go into this app, and you can see the address here if you want to check it out for yourself, it shows you what pathfinding will look like. So if I just do A-star, you can see that it finds a path. If I can also put in walls to make it search around it. And in this example, the blue squares represent evaluated nodes, and the green squares represent nodes that are candidates for evaluation. And you can see, A-star finds a way using those blue squares, a path laid out by the blue squares. And now let's take a look at jump point search. So do the same thing again, and you can see that jump point search actually takes a lot longer, but that's because of the visual effect. It's turning all the jumped over nodes gray. But the important thing to note is that there's also a lot less blue nodes, which means that a lot less nodes had to be evaluated. If you go back to A star, you can see that this entire area is filled with evaluated nodes, whereas again in jump point search, just a few nodes. It's going to take a while, but you get the idea. So what is JPS doing? What is jump point search actually trying to do? One of the goals is to deal with the symmetry in A star. So if I go back to A star, actually, let me just tell you what that means. So if this is my starting node and this is my goal node, I can take a path that goes something like this. But at the same time, I can take a path that goes like this. And these two paths are essentially equivalent because they have the same cost, and they're not broken up by walls or anything. So ideally, if we have one of these paths, we would want to ignore the other paths and not even consider them. And the fact that they're essentially the same cost and follow a very similar trajectory means that they're symmetric. And the idea behind culling those paths that are symmetric is called symmetry breaking, and that's what jump point search attempts to do. Another thing that jump point search attempts to do is to deal with the fact that a lot of times grids contain a lot of empty space. So what it'll try to do is jump over a lot of uninteresting points and only evaluate the interesting points. And the interesting points are called jump points, hence the name jump point search. And if you're interested, they have the authors of jump point search have a paper about that goes into detail on how to implement it. They even have some nice almost pseudocode-like sections, and they talk a lot in detail about how if it's equivalent in terms of optimality to A star and all that. So take a look. As a non-computer science major, it took me about 10 reads to start understanding what they were trying to do, but hopefully, maybe it'll take you a lot less. So let's get into my Unity implementation of A star and jump point search. So actually, before I do that, I want to mention that I did use the same sort of data sets for A star and jump point search to make sure that the only variable is the algorithm itself. So I'm not muddying up the comparison by using different data sets and all that, or different data structures and all that. So first, what's going to happen is that I'm going to generate a terrain. And this is some just basic Perlin noise terrain generation with a height map texture. And I'll start with A star, which I think is activated. Yep. So if I drag and click, it'll find a path from the green node to the red node. And the white nodes that are being generated are the ones that are being searched. And if we go back to, or if you recall the online app that we looked at, you'll see that the shape is pretty similar. So if I do something like this, you see that there's this kind of almost oval-like shape that goes from the start to the end. And you can see something sort of similar in A star as well. And the height actually corresponds to the score of the node, but it's sort of hard to tell. So you can see that it's taking some time. If this was a game and we told the unit to go from green to red, the green node to the red node, it'll be pretty unacceptable because it's taking, let's see, 10 seconds, 5 to 10 seconds to figure out how to get there. And if we do something even longer, it's going to evaluate a lot of nodes trying to get to that point. So I'm not even going to wait for that to finish, but you can clearly see that it's pretty slow. So let's take a look at jump point search. So I'm going to deactivate this. Alright. So regenerating the terrain, and now I'm doing jump point search. And here you can see clearly just from the start it's a lot faster. And also you can see that it's evaluating a lot less nodes. And oh, by the way, yeah, again, the white nodes are the evaluated nodes. And it's actually pretty interesting just to see the pathfinding algorithm work. It almost seems like these points are random if you don't understand what's going on, but it's pretty cool. Let's just do a couple more. And even in these longer paths, it's still taking some time, but it's clearly taking a lot less time than A* by itself. So exactly how much faster is jump point search compared to A*? We can find out, compare them directly. So I'm going to activate both. I'm going to disable the white blocks so it'll speed it up a little bit and not clutter up the screen too much. So I'm going to do that for both A* and jump point search. And I'm going to go back. So let's do a pretty short path. So jump point search took 0.15 seconds, and then A* took 3 seconds. So what is that? About a shouldn't do math. 20 times improvement. Doing another one. So jump point search took 0.1 seconds, and then A*, so that's about 50-fold improvement. And I mean, if the nodes are really close, the difference is minimal. But as you get further and further, the difference becomes pretty significant. In my experience, I've seen it go up to 200 times faster, but I'm sure you could get it. Well, I shouldn't say I'm sure. It seems likely that it'll go even further than that. And you can see here is an example of symmetry. For example, so both of these paths are essentially the same cost, but they just have different paths. So let's just do a couple more. So you can see the jump point search is completing almost instantaneously, and then A* is taking a lot longer to catch up. So yeah, about a 50 to 200-fold improvement on medium to long-ish distances. It's pretty good. To be frank though, even jump point search is kind of slow at times. For example, if I try to go across the map like this. Again, if I was playing some sort of real-time strategy game, it would be pretty unacceptable for the unit to receive an order, wait around for 3 seconds, and then start moving. So there's definitely improvements that could be made. The authors of the jump point search paper actually have followed up with a new paper that describes how to further optimize jump point search, and the authors are Daniel Haribor and Alvin Grasstein. They have a paper called Improving Jump Point Search, and you can find his site, a pretty nice site for I think it's a university, I'm not entirely sure, but they have the full text here. And it talks about how to improve jump point search by efficient data manipulation using blocks, pre-processing for jump points, and pruning jump points. So I might take a look at this and try to improve jump point search, even my implementation of jump point search even further. Hope that was interesting to you. If you're interested in pathfinding in general, I would recommend checking out this blog post from an ex-Blizzard dev who worked on the StarCraft 1 pathfinding. And if you've played StarCraft 1, you know that it had some notoriously weird pathfinding issues, and this blog post sort of explains why. Basically, it has to do with the fact that it used the pathfinding and the map engine from, or the same engine from Warcraft, which is more top-down rectangular, and try to apply it to a isometric non-rectangular world. So it ended up with some odd pathfinding issues. The most interesting part of this blog post actually is that he talks about how, again, in StarCraft 1, the worker units don't collide when they're harvesting resources, and this was actually a quick and dirty fix for the pathfinding issue that they were having, because the harvesting units would get clumped up and get jammed up. So it was never meant to be a feature. Instead it was a quick and dirty fix to deal with the pathfinding issues. So that's it. That's all I have. Let me know if you know any interesting anecdotes or stories about pathfinding, or if you've implemented jump point search in Unity yourself, if you've experienced anything weird, or any ways to improve, or maybe if you've implemented the new version of jump point search, let me know as well. So again, that's it. Thanks for watching. Bye.